Today we're talking about regression models focusing on nominal independent variables. So we've given some example questions in the past few weeks about types of questions we can answer. So we've talked about, do children's grades differ by the city they live in? Do depression levels differ by sexual orientation? And in both these example questions, your dependent variable here is something that's continuous or nominal. And then you've got a nominal, or did I say nominal? Continuous or ordinal, excuse me. And then you've got this nominal independent variable. You're looking potentially here at different groups. Then we talked about, could marital satisfaction be correlated with life satisfaction, or pro-social behavior? Is it linked with social skills? And in these two example questions, both independent and dependent variables are continuous or ordinal. So we've talked about we could use these types of questions for t-tests, in particular independent samples t-test. In here we could use regular bivariate correlations, but we can do all of these with regression, and we can do them all in a regression model all at the same time. So last week we talked about continuous and ordinal independent variables, how to focus on making those interpretations. This week we're going to focus on interpreting nominal independent variables and how we understand those regression estimates, or those betas, semi-partial correlations. So kind of graphically what we're saying is, when we're using nominal independent variables in a regression model, is, are these means different from each other? Or if we put it into a plot and did a bar graph, are the heights of these bars different from each other? So to repeat myself here, to make this essential point, with continuous and ordinal independent variables in a linear regression model, we're going to interpret those like we would correlations. But when we have nominal independent variables, we're going to interpret those as mean differences, the mean differences between groups. This is a really, really important point. All right, so you've seen this code before. It's the same as last week. You run a regression model, save it into an object, run summary on that object. That LM, right, standing for linear model. So for the last few weeks, I've been saying, or a couple weeks, the reason why we need zeros, I've been saying, just kind of hang on. And I've dropped a couple of little pieces of information about that for a while. But when we prep our variables for a regression model, we want to make sure we have a meaningful zero. The reason for that is because of the intercept. So typically when you graph a linear relationship between variables, the intercept is where it cuts on the axis. The more technical or precise definition, though, is it's where the line cuts when your x variable is 0. So here in our output, we have this estimate for an intercept right here. So this becomes our average on our dependent variable when our x variables are at 0. So going more right on that, or explaining this fully, so why again do we need to make sure we have a meaningful 0? So let's just simplify things, and let's imagine we have one independent variable, and let's for a minute pretend that it's an ordinal variable on a 1 to 5 scale. So 1, 2, 3, 4, and 5. So in this instance, where would the intercept be? So the intercept is where our line here, when it intercepts when it crosses where x is 0. Now there is no x on here, and so it's kind of like we've got to draw it out here, and this is where our estimate for the intercept would be, is where 0 on x would be. But that doesn't make sense if there is no 0 on the x variable. So we talked about mean centering, we talked about dummy codes. So if I change this, and let's say 3 had been my mean, let me just show that one more time. If 3 had been my mean, and so then I centered this, so now my mean is 0, my intercept is now here. So what that does for us is it ensures that our estimate of the intercept is within our data. It's within the scales and not off the scales. It makes that intercept usable and makes it so that it's useful, meaningful information. So like we've said multiple times, with nominal variables, what we're talking about is mean differences between groups. We're thinking of this very much like an independent samples t-test. So with these nominal variables, that intercept then becomes the mean for the group who is coded as 0. So in this model down here, we've got a variable here called male. Now remember, whatever you name the variable, the standard convention is the name of the variable is the group that's coded as 1. So 0 would be not male. So the average on, and we've got our model up here, our dependent variable is child vocabulary. So our average for non-males or for girls in this sample was 5.59 on the vocabulary score. Now, what if we want, and we could focus on the estimate too for this nominal variable. This would be the difference between the means. And because it's significant, we're saying there is a significant difference between males and females on this vocabulary score. So if you wanted um, that the mean or the average for males, if you've already created a variable called female, you could just swap this out and for the female variable, and this intercept is going to change. Or you could also do the math yourself. So the beta or the estimate or the regression coefficient, the semi-partial correlation, for that nominal variable, it's the difference between those two means. So if we were to round this, this is saying that males on average score 0.28 lower on the on that dependent variable, in this case, the children's vocabulary scores, than do females. And so we could do that math ourselves. We could do 5.59 minus 0.28, and that would give us the average for males. Okay. If you're feeling a little uneasy about that, rewind and watch again. This is a very, very important point. So I want to make, though, a connection, because last week we were talking about that regression coefficient meant if you went up by 1 on the independent variable, how much did the dependent variable change? And technically what I'm saying here is the same thing, but we talk about it differently because those independent variables are different kinds. So if I have coded my nominal variable here, and with gender being a two-level group, two-level variable, right, we've got zeros and ones. And I have you code that as a 0 and 1 so that going up by 1 means going from one group into the other. And so if that that beta for the male variable is negative 0.28, well, that is my slope. But we don't normally think of slopes when we're talking about discrete groups. So the difference between these two groups is negative 0.28, but that's also the slope. So technically it is the same thing, but again, we're thinking about this differently. If this was a continuous or an ordinal variable, we would have potentially people who were on a scale in between this 0 and 1. But with these discrete groups, with a nominal variable, these dots representing different participants, people are only in this group. We don't have anybody here in the middle on this male variable. Okay, so again, if that point is not quite clicking yet, rewind, watch again, but make sure then ask in class too. This is a really important point. We want to make sure that you get this down. So that all is nice, right? With a two-level variable, it's a lot simpler. But what about when we had these nominal variables with 3 or more groups or 3 or more levels, and we created these series of dummy codes? So we had this example of marital status or relationship status, where you had this original variable and you had these 5 different groups, and we made these 5 new variables. assuming we had enough sample size in each one. So what do we do here? Um, what you're going to do is you're going to, however many groups you have, or however many dummy codes you created, you're going to put them in the model except one. So you'll leave one of them out. So if I had these 5 dummy codes here, I'm going to put 4 of them in. So I might do, whatever my dependent variable is, I might do divorced, widowed, never married, and remarried, and I've left that married group out. Or I could pick a different one. It really doesn't, it usually, well, sometimes it depends, it matters which one, but which one you leave out is really driven by what questions you're trying to answer. Statistically, it doesn't matter which one you leave out. So why then are we leaving one of them out? Well, it has to do with 0 again, that number 0. So if we look down here at this chart, if I put in every single one of these dummy codes, these 5 dummy code variables, everybody will have been scored a 1 on at least one of those variables. That means they're not scored a 0. Nobody is a 0 on, essentially nobody is a 0. When we look at that linear model and we're plotting things out, it's easier for us to think about one variable at a time. But the model here is based on all the variables put in the model at a time. So if I put all of them, all 5 of them, nobody is a 0 on every variable. There isn't that potential. Everybody's going to be a 1 on at least one of the variables. And so then that intercept becomes meaningless. Even more than that, the model actually won't work. And I'm going to wait until we get to demonstrating this in RStudio to kind of demonstrate what I mean there. But it creates this problem called multicollinearity that stops the model actually from working. Now, some key just terminology here. Is that we call the one that we have left out the reference group. So next week we're going to talk about how do you report on regression findings, how do you talk about them, and what we're going to do is write something called an analytic strategy. And you'll often see in those strategies somebody will say, and the reference group was this. When they say what a reference group is, that's referring to the group that got left out, the one that was left off. So like in this example up here, if we left married out of it, that would be the reference group. Now, what if, well, okay, so let's back up and say another thing about this. So the estimates or the betas then for each of these variables, they are the mean difference between that group and the reference group. So the estimate for divorced would be what's the mean difference between those who are divorced and those who are married. The estimate for those who are widowed would be what's the mean difference between those who are widowed and those who are married, and down the line. But sometimes maybe after running that, you're like, oh, but I really want to compare those who are divorced versus those who are widowed, or something like that. To do that, all you do is you just change what your reference group is. So before we had the divorced group here, we could take them out and put the married group in. And now the estimate for widowed will compare those who are widowed to those who were divorced and never married to divorced, and here remarried to divorced. All right. So let's jump over to RStudio and let's demonstrate what this looks like. I've already got a script kind of set up and going here. We're using that same vocab data set that we've used the last 2 weeks. Again, this is a simulated data set, and we've got a variable here called female, because the original one only had a variable called male, so we're adding one called female. We've already dummy coded things. We've already done our centering, our continuous and ordinal variables. So the data set here is ready to go. So let's talk about if we're looking at 2-level nominal variables. Let's do, I'm just going to call it model 2, LM. It was vocab. I struggle with names. Vocab, ready. Child vocab. So what I did here is I typed in names and the name of the data set, and it just prints out all the names so that I can copy and paste those. Remembering that copy and paste is your best friend. So we're gonna demonstrate a couple of things here, and then what I'm going to do is leave the code in that is like the best or the right code to use. So I'm going to run this model first with this child sex variable, and that's what it was originally in the data before it was prepped. And you'll notice we had 1s and 2s, and then we changed that into this male variable where 1 was male and 0 is female, and then a copy of that where 0 is male and 1 is female. So what I want to demonstrate here is how the intercept changes based on what variables you, or how your variables were prepped. Data equals vocab, ready. Okay, so let's run that. Okay, so if we run that with that child sex variable and then we look at our output, we're going to see here that our intercept is 4.27, right, rounding to 2 decimal places, and there is a mean difference between boys and girls. Here showing that girls were scoring on average 0.71 higher on that vocabulary measure. So what I want to do now is we're going to run a copy of that, but we're going to change that child sex variable to male. And we're going to compare it here to that output. Okay, so when we ran it with the child sex variable, where things were coded a 1 and a 2, what we had was the intercept was 4.27. And we change it now to a model where we use, instead of the child sex variable, the male variable, where they're now 0s and 1s, and 1 being male. So now our intercept estimate is 5.6 or 5.7, if we round that. So the estimate for the intercept in that first model wasn't really usable, because this is the estimate if the variable was coded at 0, but nobody was coded 0. And so that estimate doesn't actually refer to anybody who could potentially be in our data, versus in this case where we've prepped this male variable so that 0 means female, this intercept now means the average for females. I may have said that wrong just a second ago about it being for males. It's the average for females, because it's whatever group is coded as 0. What does then this number here refer to? It's the difference between males and females. And something you'll notice is that the sign is flipped from positive to negative, but it's the same number that we had before. The p-value is the same, the standard error is the same, the t is the same, although the t-value here is swapped from positive to negative. But we're getting the same effect essentially for the gender variable, even though we've recoded it. So the key point there is when we recode things, prep them for a regression model, it doesn't change whether an independent variable is going to be significant or not. What it does is it changes the intercept, and it makes that intercept now a usable, meaningful number. Like when you ran independent samples t-test, you wanted to know what were the means for both groups. So now we have here the mean for females. If I want to know what the average was for males, I could just do 5.7 minus 7.1, or we could, let's do one more iteration of this, change it from the male variable to the female variable. And if we look at that, now the intercept estimate is the average for males, because with this female independent variable, 0 is for males. What's the difference between males and females? This has now gone from negative to positive, because here going from 0 to 1 means males to females, and here means females to males. So those are just going to be flipped. But you've got, again, the intercept for males, you've got the intercept for females. So is there an average difference in the vocabulary scores of boys and girls? Yes. Well, what was the average for females? Or for girls? It was 5.7. What was the average for boys? 4.98. So again, this is very much like an independent samples t-test. And if we went and ran an independent samples t-test, you're going to get the same answer. But the reason why we're doing this in a regression model is because then we can control for other things. So let me, let's scroll up to our list of names. Let's control for the quality of the child care center and the quality of the parent education level. So if we run those, our effect here then of males has gone down, or of gender. Remember that the estimate for gender before was like 0.71. Now it's 0.28 or negative 0.28. The reason being is that we've controlled for things. We've partialed out some of the variation accounted for by parent education and child center quality, and this is what's left over of gender. So gender still matters, but just not as much as we thought. How then do I interpret the estimate of the intercept when I have included these other things in it? Well, if we want to be technical, it's the average when all of our independent variables and control variables are at 0. So bear with me for a second as I walk through this. So the average vocabulary scores, or the average vocabulary score is 5.58. If we're rounding that for females, because that's what 0 is on this variable. For females who go to child care centers who have average quality and whose parents had average education. That's because these are the centered versions of those variables where we made the average into 0. So technically this is for all of the variables. It's not very often though that you hear people talk about this and say, well, here is the average for females with average center quality, with average education, right? And maybe they controlled for other things with average income and who were from this neighborhood and had average number of siblings. You often don't hear that. Rather, if these were control variables, the most common way you might say this is you might actually just leave those out and say, well, the average for females was this. Or you might say, after controlling for parents' education and the quality of the child care center, the average for females was 5.58. And if we wanted that for males, right, we would just change that variable around and we'd say after controlling for child center quality and parent education, the average for males was 5.29. And females or girls in this sample had higher vocabulary scores than boys. All right, let me just add a note here with a 2-level nominal variable. Use a prepped one that codes the groups to 0 and 1 so that your okay. So with 2-level nominal variables, that's it. And it's not uncommon when you're reading published research to see people recode things so that they always have 2-level nominal variables and not use the more complex 3 or more. And that's where we're going to go next. But I want to highlight something about this gender variable, the male-female one, that's going to help us hopefully understand some of the nuance with here these more complex 3+ level variables. So here on line 28, I'm just verifying that my recoding worked with this male and this female variable. The thing is about this male and this female variable, they're really the same variable, right? We just recoded it, so it just looks a little different. One of them, 0 is female and the other one is male, and then vice versa on the other one. But they're really the same variable. Like if you know how many females there were on the female variable, you know how many females there were on the male variable, because it's the same variable. That's an important point as we think about these more complex dummy codes. So if we're going to use this ethnicity variable, we had 4 groups: Black, Hispanic, Other, and White. And when you use, I'm going to write this note out here. When you include a nominal variable with 3 or more groups, only use one of the dummy codes. The way you'll often hear or see this written is they'll be like k minus 1. So they'll say you need k minus 1 groups. So if I have 5 groups, I need 4 dummy codes. If I have 10 groups, I need 9 dummy codes. If I have 3 groups, I need 2 dummy codes. Now, why I showed you this information on the male and female variable is because with a 2-level group, it's technically the same. We have 2 groups. I'm only going to use one of those variables. It just feels more complicated when I have more groups, even though it technically is the same. So let's, I'm going to copy this model here, and we're going to change it to model 3, and let's run names again. Okay, so we're going to leave white out of it. We're going to leave white as our reference group. And for now, we're just going to include the dummy codes for the nominal variable. So we've got Black, Hispanic, and Other. So if I run that, okay, we've got a lot of important or useful information here. So the intercept is the average vocabulary scores for the reference group. In this case, meaning those who are white, because they're the ones we left out. So another way to say that is the only people who are coded a 0 on every variable in this model are those who are white, because if they were black, they were coded 1 on this variable. If they were Hispanic, they were coded 1 on this variable, or if they marked their ethnicity as other, they were coded as a 1 on this variable. So those who are white are the only ones who are 0. So that means the estimate of the intercept is the average for those who are 0 on all the variables. We could look at the individual estimates here and ask, are there mean differences between the black children and the white children? No, right? Our p-value is greater than 0.05, so we're going to fail to reject that null hypothesis and conclude that there is no mean difference between black and white children. What about Hispanic children? Well, the p-value here is less than 0.05, so yes, on average, they have lower vocabulary scores than the white children. If we wanted to get then the average for the Hispanic children, we could do the math. We could do, sometimes I even just literally copy and paste that down into the console. So the average for the Hispanic children was 5.12. I could also come up here and change out the Hispanic variable for the white variable, and it's going to change my intercept. So now the intercept refers to children who are Hispanic. Let's go back to what we had though for a second. What about other children whose ethnicity was other? Yes, there's a mean difference between them and the white children, with those who marked their ethnicity as other being higher than children who were white. So it does feel more complex than when we had that two-level nominal variable, because we have to wade kind of through each variable at a time. We have to keep in mind what our reference group is. Like, that's a really important point, so that we know what this intercept or the estimate here is comparing itself to. What if I wanted to compare Black and Hispanic children? Then all I need to do is I need to take out one of those groups and replace it with the reference group, or make one of those groups the reference group. So if I change it and make Black the reference group, what you're going to see is that this intercept, or this estimate for the Black variable, is going to stay the same number. It's just going to become positive, because this one is comparing Black and white children. But if I change this variable to white and make Black children now the reference group, this will just flip its sign. But these two variables are going to change their estimates completely, because it's no longer Hispanic compared to white children or other compared to white children. It'll be Hispanic compared to Black and other compared to Black. So let's try that. So sure enough, all right, we had negative 0.12, we now have positive 1.2. But the estimates for Hispanic and other have changed, because this is the comparison between Hispanic children and Black children and other children and Black children. And those ones are not significant. So whichever group you make your reference, it really is which group do you want to compare to the others. And if you want to do lots of comparisons, then you're going to need to change those dummy codes around. Okay, I want to just demonstrate what happens if we put all four groups in. So on that ethnicity variable, we had four groups: Black, white, Hispanic, and other. And I've been telling you, right, K minus 1, you leave one of the groups out. What happens though if we don't? Well, what happens is that R leaves one of them out for you, and it takes the last one. Why does it do that? How does it know to do that? It has to do, again, with the idea that if we have all of those variables in there, there's nobody in the data who has coded a 0 on every variable in the model. So we have to leave one of them out. R recognizes that. The term is multicollinear. It recognizes them all as being perfectly correlated. Or another way to say that is, if you think of this as a logical puzzle, if I give you the data on the Black variable, white variable, Hispanic variable, and I tell you, okay, there is one other variable called other, people can only be coded a 1 on one of those variables. So they can, right, if they're coded a 1 on a Black, they have to be 0 on everything else. So if I give you the information on those first three variables, you know the information for that fourth variable. You don't need to see it. You could come up with that based on the information from the first three. And so when we add that fourth variable, R is saying, whoa, this is redundant information. I can't include redundant information. It creates problems. And so it excludes one of them for you. So let's take that back out. I'm going to add another note here. Okay, so like we did with the two-level nominal variables, we could then come in and add more control variables. And this can get like fairly complex, right? You can add, as long as you have at least 20 cases, or 20, your sample size is at least 20 for every variable in your model, you can add more variables. We could even add the male variable here and have things be more complex. So I can have this mix of both continuous and ordinal and nominal variables. That's totally okay. It does make then interpreting this estimate of the intercept just a little trickier, because you need to pause and think, okay, what does a 0 mean? If somebody's a 0 on all of these variables, what does that mean? Because this is the average for people who are coded as 0 on every variable. But the key point there is, right, you can mix and match lots of different types of variables. For the example code, I'm just going to leave it as the 3 dummy codes and nothing else. So that's it. Looking forward to working on this in class, and we'll see you then.